Hello, my friend. Tonight, we're traveling back to the beginning of the universe, to the Big Bang, the first light, the first stars, and the long story of how everything began. So get comfortable, relax, and let this quiet journey through cosmic history carry you gently into sleep. Chapter 1. What the Big Bang really means. When people hear the phrase the Big Bang, they often imagine a giant explosion erupting into darkness, as if the universe began like a firework going off in an empty void. That picture is dramatic, but it is not what modern cosmology means. In science, the Big Bang does not describe an explosion of matter into pre-existing space. It describes the early history of a universe in which space itself was once far hotter, far denser, and far more uniform than it is now, and has been expanding ever since. The theory is not a mythic story about a blast at one location. It is a physical model of how the observable universe has changed over time. That difference matters because the Big Bang is really a theory of cosmic evolution. It tells us that if we look at the universe today and trace its expansion backward, we arrive at a state in which galaxies were much closer together, temperatures were enormously higher, and matter existed in forms very different from the atoms, stars, and planets we know now. The model does not simply say that the universe is expanding. It says that the large-scale universe has a history. It cooled, changed, and developed structure over time. In that sense, the Big Bang is not mainly about a bang. It is about transformation. One of the most important ideas to understand is that there is no ordinary center of the expansion. When a firecracker explodes, fragments fly away from one central point into surrounding air. But the universe is not expanding that way. On very large scales, the expansion is happening everywhere. Every distant region sees other distant regions receding, not because galaxies are rushing away from a single place in static emptiness, but because the distances between large regions of space are increasing. That is why scientists often say the universe is not expanding into something else in the usual sense. Rather, space is stretching, carrying galaxies along on the largest scales. This can feel strange because human intuition was shaped inside a small world of rooms, roads, oceans, and skies. In everyday life, almost everything expands into a surrounding environment. Smoke spreads into air, ink spreads into water, debris spreads into open space. The universe is different because the framework in which distances are measured is itself dynamic. Modern cosmology, built on general relativity, allows space to expand, curve, and evolve. So when we say the early universe was smaller, we do not mean it was a little object sitting inside a larger arena. We mean that the distances between regions of space were compressed compared with what they are now. The Big Bang model also does not necessarily mean that science has already described the absolute beginning of everything. This is another place where the popular image can mislead. The standard Big Bang model works extremely well when describing the universe from a very early hot, dense phase onward. It is strongly supported by evidence such as cosmic expansion, the cosmic microwave background, and the observed abundance of light elements. But when people ask what happened at the very first instant or what came before, physics becomes much less certain. Some scientific models include inflation before the hot dense phase we usually discuss, and some explore deeper quantum ideas, but there is not yet a complete, experimentally confirmed theory of the ultimate beginning. So the phrase Big Bang names a successful framework. not a final answer to every metaphysical question. It is best understood as the theory that the universe, as we can investigate it, emerged from an early state that was extremely hot and dense, then expanded and cooled, allowing particles, nuclei, atoms, stars, galaxies, and eventually planets to form. This is why the Big Bang matters so much. It connects the vastest visible structures in the sky to microscopic physics in the earliest cosmic moments. It turns the universe from a static backdrop into a story with stages, transitions, and measurable relics. A major reason scientists accept this picture is that the universe still carries traces of that early state. One of the clearest is the cosmic microwave background, the faint afterglow of the early universe. In the first part of cosmic history, matter and radiation were coupled in a hot, opaque plasma. Light could not simply travel freely across the universe because it was constantly scattered. Later, as the universe expanded and cooled, atoms formed and space became transparent enough for light to travel long distances. That ancient light still exists today, stretched by expansion into microwave wavelengths. It is one of the strongest pieces of evidence that the universe really did pass through a much hotter, denser phase. Another reason the Big Bang model is so powerful is that it explains why the universe contains the simplest chemical elements in the proportions we observe. In the first minutes of cosmic history, conditions allowed the production of light nuclei, such as hydrogen and helium, along with tiny amounts of a few other light elements. Much later, stars would forge heavier elements, but the early universe set the initial chemical pattern. This is a remarkable feature of the theory. It means the Big Bang is not only about distant galaxies or abstract mathematics. It is tied directly to the material composition of the cosmos. Still, the word bang has survived because it is vivid, memorable, and historically entrenched. It was not originally meant as a careful scientific description. In fact, the term was popularized in a dismissive way by Fred Hoyle, who supported a competing steady-state view of the universe. Yet the name remained, even though many scientists have pointed out that it encourages the wrong image. NASA's recent public explanations explicitly note that the phrase is misleading if it makes people picture a localized explosion with a center. In that sense, one of the first tasks in learning cosmology is unlearning the ordinary picture suggested by the name itself. It is also helpful to understand what the Big Bang does not say. It does not say that galaxies were originally blown apart like shrapnel. It does not say that empty space was waiting around before the universe arrived. It does not say that everything we see now was once compressed in the ordinary mechanical sense, like matter packed into a box. And it does not say that modern science has already solved the question of why there is something rather than nothing. Instead, the theory describes the evolution of the observable universe using the evidence we actually have. It is a scientific model, careful in some places, uncertain in others, and always tied to observation. The deepest strength of the Big Bang theory is not that it sounds dramatic. Its strength is that it makes testable predictions. It predicted, in advance, that a relic glow from the early universe should exist. It gave a framework in which expansion, cooling, and early element formation all fit together. Later observations confirmed those expectations with increasing precision. Missions such as COBE, WMAP, and Planck measured the cosmic microwave background in extraordinary detail, revealing tiny variations that later grew into the large-scale structure of galaxies and clusters. Those observations did not merely decorate the theory, they helped establish it as the central model of modern cosmology. Even so, the Big Bang model leaves important questions open, and that is part of what makes it scientifically alive, rather than mythically finished. Cosmologists still investigate what caused the earliest rapid expansion, often called inflation, what dark matter is, why the universe contains much more matter than antimatter, and how gravity behaves under the most extreme quantum conditions. A good scientific theory is not weakened by leaving room for further work. On the contrary, it gives us a stable map of what we know, while showing us where the unknown begins. The Big Bang does exactly that. There is also a quiet philosophical shift hidden inside this theory. For most of human history, the sky seemed timeless. The stars looked fixed. The heavens appeared permanent. The Big Bang changed that picture by revealing that the universe has a measurable past. The cosmos is not merely a stage on which change happens. It is itself something that has changed. Space has a history. Light has a history. Even the conditions that allowed galaxies to form belong to a sequence that can be studied. This is one of the most profound achievements of science, turning the universe from scenery into process. And yet, for all its scale, the idea can be understood in a simple way. The Big Bang means that the universe we inhabit was once hotter, denser, and smoother, and that it has been expanding and cooling over cosmic time. As it did, light was released, matter settled into atoms, gravity slowly gathered material into stars and galaxies, and the long structure of the cosmos began to emerge. Everything familiar in the night sky belongs to that unfolding. The theory does not tell us everything, but it tells us something astonishingly real. The universe has not always looked the way it looks now. That is what the Big Bang really means. Not a burst in empty darkness, but the early evolution of space itself. Not a simple explosion, but the opening chapter of cosmic history as physics can currently describe it. And perhaps there is something calming in that thought. The universe has been changing for ages beyond ordinary imagination, quietly unfolding according to deep and discoverable patterns. Tonight, you do not need to solve all of it. You can simply rest inside that larger story and let the weight of the day grow a little lighter beneath the vast, patient history of the cosmos. Chapter 2. The Universe Before the Big Bang Ideas. Before scientists began speaking about a hot early universe, many people assumed that the cosmos in its largest structure had always existed in roughly the same form. This was not a careless belief. It grew naturally from ordinary experience. Human beings look up and see patterns that seem stable across generations. The stars rise and set, constellations return, the sky appears orderly, almost permanent. For most of history, the heavens looked less like a changing physical system and more like a vast backdrop behind earthly life. The earliest serious ideas about the universe were therefore often built around endurance, balance, and repetition rather than origin and development. In the ancient world, different cultures created very different cosmologies, but many shared one basic feature. The cosmos was understood as ordered. In the Greek philosophical tradition, the heavens were often treated as more perfect and less changeable than the earth below. Aristotle described a universe in which the celestial realm followed an eternal and nearly unaltered order, while change and decay belonged mainly to the earthly domain. This distinction shaped thought for centuries. Even when later astronomers revised the geometry of the cosmos, The sense that the universe on the largest scale should be timeless remained deeply influential. That preference for a stable universe survived well into modern science. When astronomy became more mathematical, and when the works of Copernicus, Kepler, Galileo, and Newton transformed our understanding of motion, gravity, and planetary structure, they did not immediately produce a modern theory of cosmic history. Newton's law of gravity allowed scientists to think about how matter attracts matter across vast distances, but it also raised difficult questions. If the universe contained matter everywhere, why had everything not already fallen together? If it stretched infinitely far, how should gravity behave on the largest scales? These puzzles showed that a full cosmology required more than local physics. It required a theory of the universe as a whole. There were also observational reasons for caution. Even by the 19th century, astronomy had become powerful, but the scale of the universe was still poorly understood. Many objects in the sky that we now know are galaxies were once grouped under the broad category of nebulae. Their distances were uncertain. Their nature was debated. Without a clear picture of the structure beyond the Milky Way, the question of whether the whole universe changed over time remained difficult to frame properly. A famous example of tension in the older worldview appeared in the problem later associated with Heinrich Olbers. If the universe were eternal, static, and filled more or less uniformly with stars, then the night sky might be expected to glow much more brightly than it does. The fact that the sky is dark hints that one or more of those assumptions must fail. Today, the darkness of the night sky is understood in the context of cosmic expansion and the finite age of stars and galaxies as we observe them. But before modern cosmology matured, such problems served as warnings that the old intuitive picture of an eternal static universe was not entirely comfortable, even on logical grounds. The decisive shift began only when gravity itself was rethought. In the early 20th century, Albert Einstein replaced Newton's gravitational force with a deeper description in which mass and energy influence the geometry of space-time. General relativity provided, for the first time, a framework capable of treating the universe dynamically on the largest scales. Yet, when Einstein first applied it to the cosmos, he did not accept the consequence that the universe might expand or contract. Like many thinkers before him, he expected the large-scale universe to be static. To preserve a static cosmic model, Einstein introduced an additional term into his cosmological equations, now known as the cosmological constant. Its role in that early context was to counteract the attractive tendency of gravity and hold the universe in overall balance. This choice tells us something important about the scientific imagination of the time. Even with a theory that naturally allowed change on the largest scales, the dominant instinct still leaned toward permanence. A changing universe felt radical. A static universe felt philosophically and visually more natural. But the equations of general relativity did not quietly accept that preference. Soon, other researchers began to explore solutions in which the universe changes with time. Willem de Sitter found a model with very different large-scale behavior from Einstein's matter-filled static cosmos. More importantly, Alexander Friedmann showed that Einstein's equations admitted expanding or contracting universes without requiring a static balance at all. Friedmann's work was mathematically profound because it suggested that cosmic evolution was built into the structure of the theory itself. A universe could have a history, At first, these dynamic solutions did not instantly transform astronomy. Mathematical possibility is not the same as observational acceptance. The older static picture still felt intuitively compelling, and the available evidence had not yet forced a complete change of view. Yet, the door had opened. Once expansion became a legitimate theoretical outcome, scientists could begin asking a new kind of question. If the universe is changing now, what was it like earlier? This is where Georges Lemaitre became one of the central figures in the history of cosmology. Working from general relativity and astronomical observations, he argued that the universe is expanding and connected this idea to the observed recession of distant galaxies. In later work, he went further and proposed that the cosmos may have emerged from an extremely compact early state, sometimes described through his famous image of the primeval atom. This was not yet the modern Big Bang model in its full developed form, but it was one of the first major attempts to imagine the universe as having a genuine physical past that differed radically from its present. Lemaitre's contribution is especially important because it joined theory and observation. He was not simply speculating that a beginning would be philosophically interesting. He was working within relativity and taking seriously the astronomical evidence that space itself might be changing. This combination helped cosmology mature into a true physical science. It moved discussion away from pure metaphysical preference and toward a model constrained by data. Then came the observational breakthrough most closely associated with Edwin Hubble. By measuring the light from distant galaxies, astronomers found a systematic relationship between distance and redshift. The farther away a galaxy is, the more its light is shifted toward longer wavelengths, consistent on large scales with cosmic expansion. This did not mean that every galaxy behaves like a fragment blown outward from a central blast. Rather, it supported the conclusion that the large-scale fabric of the universe is expanding. Once this picture became difficult to dismiss, the old static universe lost much of its remaining security. Even then, the Big Bang idea was not instantly accepted in the modern form familiar today. Scientific theories rarely become established in one dramatic moment. They compete, evolve, absorb new evidence, and survive criticism only if they continue to explain the world better than their rivals. In the middle of the 20th century, one major rival was the steady-state theory, developed by Fred Hoyle, Hermann Bondi, and Thomas Gold. In that picture, the universe expands, but its average large-scale appearance remains the same over time because new matter is continuously created. The steady-state model preserved an eternal cosmos while accommodating expansion, and for a period, it attracted serious support. This stage in the story is important because it reminds us that cosmology was never a simple march from ignorance to certainty. Scientists were choosing between models that each tried to honor part of the evidence while preserving different underlying intuitions. The steady-state picture preserved cosmic timelessness. The evolving universe picture embraced a changing large-scale history. Both were scientific in the sense that they aimed to describe the real universe and could be compared with observation. Nature's decision became clearer as evidence accumulated. Observations of radio sources and distant cosmic populations began to suggest that the universe did change over time in ways not easily reconciled with a perfect steady state. Most decisive of all was the discovery of the cosmic microwave background, a faint bath of radiation filling the universe. This background had been predicted as a relic of a hot early phase in an evolving universe. When it was detected, it provided strong support for the view that the cosmos had once been much hotter and denser than it is now. Seen from a distance, the older belief in a static or eternal universe was not foolish. It was an understandable starting point, built from limited evidence, philosophical inheritance, and the apparent stability of the sky. The achievement of modern cosmology was not simply that it announced something surprising. It was that it found ways to test surprise against reality. The universe turned out not to be fixed scenery. It turned out to have a thermal past, an evolving structure, and a history written into light itself. That transformation in thought is one of the great quiet revolutions in science. It changed the question from what arrangement does the universe have to how did the universe become what it is? Those are very different questions. The first can sometimes be answered with a snapshot. The second requires a narrative grounded in physics. Once that change occurred, cosmology became historical as well as mathematical. The universe was no longer only something to describe, it was something to reconstruct. And perhaps that is part of why this story still feels so powerful. For so long, human beings imagined the heavens as the symbol of permanence, only to discover that even the universe has a past. The stars above us are not just distant lights, they are late chapters in a much older unfolding, and there may be something quietly existential in that realization. That change is not a small local accident of human life, but part of the deepest nature of reality itself, and that our brief awareness exists inside a cosmos that has been remaking itself long before us and will continue long after us. Chapter 3. How scientists discovered that the universe is expanding. For most of human history, the sky did not look like something that was growing, drifting outward, or changing on the largest scales. It looked stable. The stars returned in familiar patterns, and even when astronomers learned that planets wandered against the background of the constellations, the universe as a whole still seemed more like a permanent stage than a changing physical system. The discovery that the universe is expanding was therefore not a simple correction to one detail of astronomy. It was a deep change in how reality itself was understood. It turned the cosmos from a fixed arrangement into an evolving structure with a measurable past. That discovery did not happen in a single moment, and it was not made by one observation alone. It emerged gradually through a combination of improved telescopes, better methods for measuring distances, careful studies of the light from distant objects, and a new theoretical framework provided by general relativity. In that sense, the expanding universe was not merely seen. It was assembled from clues. Each clue on its own might have remained uncertain. Together, they formed one of the most powerful conclusions in modern science. One of the first great steps toward this conclusion came from a question that now sounds surprisingly basic. What exactly are the faint spiral nebulae in the sky? In the early 20th century, astronomers could see many cloudy, spiral-shaped objects through large telescopes, but they did not yet know whether these were nearby structures inside the Milky Way or enormous star systems far beyond it. That uncertainty mattered enormously. If the Milky Way was the whole universe, then cosmology would be a very different subject than if the universe contained countless other galaxies spread across vast distances. Edwin Hubble helped resolve this question by studying stars in the Andromeda Nebula and showing that it was far beyond the size of the Milky Way. This meant that Andromeda was a separate galaxy and that our own galaxy was not the entire cosmos. The universe had suddenly become much larger. That enlargement of the universe was essential because once astronomers knew that galaxies existed beyond the Milky Way, they could begin comparing those galaxies to one another on cosmic scales. But to do that, they needed reliable ways to estimate distance. This was one of the hardest problems in astronomy. Nearby objects can sometimes be measured geometrically, but distant galaxies required a chain of methods, each extending the reach of the one before it. One crucial tool was the study of Cepheid variable stars. This changing brightness follows a pattern that reveals their true luminosity. By comparing how bright such stars truly are with how bright they appear from Earth, astronomers could estimate how far away they must be. Hubble used Cepheid stars to determine distances to galaxies, turning vague smudges of light into objects placed at meaningful locations in space. Distance alone, however, was not enough. Astronomers also needed to know how those galaxies were moving relative to us. For that, they studied light itself. When light from an astronomical source is spread into a spectrum, it contains characteristic features associated with particular elements. If those spectral features appear shifted toward longer wavelengths, the light is said to be redshifted. Earlier astronomers, such as Vestos Slipher, had already measured redshifts for many spiral nebulae and found that a large number of them appeared to be moving away from us. This was an extraordinary clue, but at first it was incomplete because the true distances to those objects were still uncertain. Once distance estimates improved, the meaning of the redshifts became far more powerful. The key insight came when galaxy distances were compared with their redshifts. Hubble, working with redshift measurements that had been obtained in part by Milton Humason, found a systematic relationship. On large scales, the farther away a galaxy was, the greater its redshift appeared to be. In simple terms, distant galaxies were receding faster than nearer ones. This was not just a pattern among a few unusual objects. It pointed toward a general rule. Space on the largest scales was not static. The universe was expanding. NASA's historical summaries credit Hubble with confirming the expansion in the late 1920s, using this combination of galaxy distances and redshift measurements. What made this finding so profound was that it was not best understood as ordinary motion through fixed space, like sparks flying from a fire. On cosmic scales, the recession of galaxies is better described as the growth of space itself. As the universe expands, the light traveling through it is stretched to longer wavelengths, producing what is known as cosmological redshift. Modern NASA explanations emphasize that this is not identical to a simple everyday Doppler effect, though the two ideas are related in spirit. The recession pattern is a sign that the large-scale geometry of the universe is changing over time. That shift in interpretation was one of the most important conceptual steps in cosmology. The observational discovery also aligned with theory in a remarkable way. General relativity, Einstein's theory of gravity, had already opened the possibility that the universe might not remain fixed forever. In fact, as later historical accounts from ESA explain, the equations naturally allowed a universe that changes, even though the common view at the time favored a stationary cosmos. Einstein had initially tried to preserve a static universe by adding an extra term because a changing universe felt too radical. But the mathematics did not truly prefer stillness. Researchers such as Alexander Friedman and Georges Lemaitre explored solutions in which the universe expands or contracts. Lemaitre, in particular, connected the theoretical possibility of expansion to the astronomical evidence and even provided an early estimate of what later became known as the Hubble constant. This is why the history of the expanding universe should not be told as a story of theory defeating observation or observation defeating theory. It was a meeting point. The equations of general relativity made a dynamic cosmos scientifically imaginable. The telescopes and spectral measurements made it observable. Without the theory, the redshift pattern might have seemed mysterious or incomplete. Without the observations, the theory might have remained a mathematical curiosity. Together, they changed cosmology into a physical science of cosmic history. Even so, the idea of expansion did not instantly settle every debate. Some astronomers remained cautious about the distances, the interpretation of redshift, and the broader implications. Science often moves this way. A major conclusion is first recognized as plausible, then increasingly hard to avoid, and only later accepted as foundational. The expanding universe passed through that process over time. Yet once the distance-redshift relation became clear, the older picture of a universally static cosmos lost much of its stability. If galaxies are, on average, receding from one another on large scales, then the universe cannot have always looked exactly as it does now. It must have been denser in the past. That realization opened the road toward modern Big Bang cosmology. Later discoveries made the case even stronger. The cosmic microwave background and the observed large-scale structure of the universe showed that expansion was part of a much deeper story about a hot early state and the growth of cosmic structure over time. But the original discovery of expansion remains special because it changed the direction of thought. It told scientists that the universe was not a finished arrangement to be mapped once and for all. It was an unfolding process. The farther outward astronomers looked, the more they were also looking backward into a changing past. Modern astronomy has refined the measurement of cosmic expansion far beyond the first distance redshift plots. Space telescopes, supernova surveys, and precision measurements of the cosmic microwave background have transformed expansion from a bold discovery into a field of exacting research. Astronomers now investigate not only whether the universe expands, but how fast it expands, how that rate has changed over time, and why the expansion today appears to be accelerating. NASA and ESA both describe this later work as part of the continuing effort to understand dark energy and the expansion history of the universe. In other words, the original discovery was not the end of the story. It was the beginning of a much larger scientific journey. There is also something beautiful in how indirect this discovery was. No astronomer stood outside the universe and watched it swell from the outside. No one saw galaxies moving away across some cosmic edge. Instead, human beings on one small planet studied flickers of light, patterns and spectra, and the behavior of a special kind of star. From those quiet clues, they learned that the entire large-scale universe is changing. This is one of the great strengths of science. It does not need a privileged view from nowhere. It can begin locally and still reach truths of enormous scale. The discovery of expansion also changed the emotional shape of the cosmos. A static universe can feel monumental, but it is also strangely closed, as if everything important has already been arranged. An expanding universe is different. It has direction, history, and development. It allows the idea that the universe we see today emerged from earlier conditions that were not at all like the present. Galaxies, stars, atoms, and even the transparency of space belong to a timeline. Once astronomers understood expansion, the sky stopped being only a ceiling of lights. It became evidence. And perhaps that is why this discovery still feels so quietly overwhelming. By measuring the light of distant galaxies, scientists learned that the universe is not standing still around us. It is opening outward on the grandest scales, and every deep observation is also a glimpse into time. There is something existential in that realization, that the cosmos is not a frozen backdrop for human life, but a living history in motion, and that our brief awareness has arisen late within an expansion that began long before we were here to notice it. When the day has been noisy and narrow, it can be calming to remember that reality is larger and older than any one moment of worry. The universe has been unfolding in silence across unimaginable distances, and tonight you are allowed to rest for a while inside that vast, patient motion. Chapter 4: The First Moments of the Universe. If the discovery of cosmic expansion taught scientists that the universe has a history, then the study of its earliest moments opened the most difficult part of that history. Looking backward through cosmic time does not simply take us toward a smaller version of the present universe. It takes us toward a state so hot, dense, and energetic that many of the familiar structures of nature had not yet emerged in the forms we know today. At those earliest times, there were no stars, no galaxies, no atoms, no planets, and no chemistry. Even the ordinary distinction between the peaceful darkness of space and the bright objects within it would have made little sense. The young universe was not a stage waiting to be filled. It was an extreme physical state in which the basic conditions for later structure were still being established. This is also where scientific confidence becomes more delicate. Cosmologists do not claim to possess a complete description of the absolute beginning in a final sense. The farther back they try to go, the more they encounter limits in current theory, especially where gravity and quantum physics must both matter at once. There is still no fully confirmed theory of quantum gravity that describes the deepest, earliest regime with complete certainty. So when scientists describe the first moments of the universe, they are not speaking with equal confidence about every stage. Some intervals are strongly grounded in observation and well-tested physics. Others are plausible frameworks supported indirectly by data, but not yet confirmed in every detail. That distinction is part of what makes early universe science careful rather than mythic. One of the leading ideas about the earliest accessible phase is inflation. In this picture, the universe underwent a very brief period of extraordinarily rapid accelerated expansion in its infancy. Inflation is not just an attempt to make the beginning sound dramatic. It was proposed because it helps explain several features of the universe that otherwise look puzzling. It offers a reason why the large-scale universe appears so geometrically close to flat, why regions now separated by immense distances share nearly the same average properties, and why tiny primordial irregularities existed from which later cosmic structure could grow. Modern space-based observations of the cosmic microwave background strongly support the broader inflationary picture, even though the detailed mechanism behind inflation remains uncertain. Tiny fluctuations observed later in the cosmic background are understood as relics of very early irregularities that were stretched to cosmic scales. That point is essential. The early universe was not perfectly smooth. It was extremely uniform on large scales, but not absolutely featureless. Very slight differences in density were present. These tiny variations would later become enormously important because gravity could slowly amplify them over time. The rich web of galaxies, galaxy clusters, and vast cosmic structure seen today appears to have grown from those small primordial seeds. In that sense, the first moments of the universe were not only about heat and compression, they were also about pattern. The earliest cosmos contained the faint unevenness from which all later structure emerged. After this earliest rapid phase, the universe is understood to have entered a hot, dense state filled with energy, radiation, and elementary particles. NASA's overview of cosmic history describes the universe in its first second as an extremely hot primordial soup of light and particles. This is a useful image, provided it is understood scientifically rather than poetically. The young universe was so energetic that matter could not yet settle into the more stable composite structures familiar from later times. Conditions were violent, crowded, and constantly changing. Particles were created and destroyed in interactions happening throughout space. Matter and radiation were tightly coupled in an environment where nothing like atoms or transparent emptiness could yet exist. In these very early conditions, the fundamental ingredients of matter behaved differently from the way they do today. Quarks, which now are permanently confined inside protons and neutrons under ordinary conditions, are thought to have existed in a deconfined state along with gluons, forming what physicists call a quark-gluon plasma. CERN describes heavy ion collision experiments as a way of studying this remarkable state of matter, because it resembles the conditions of the early universe before quarks became locked into hadrons. This means that the first moments of cosmic history are not purely inaccessible to experiment. Scientists cannot recreate the universe itself, but they can reproduce tiny droplets of matter under comparable physical conditions and learn how such matter behaves. That connection between particle physics and cosmology is one of the great achievements of modern science. The earliest history of the universe can be investigated partly in the laboratory. As the universe expanded, it cooled. This cooling was not like a hot object losing heat into a colder environment outside itself. There was no external room into which the young universe could vent its energy. Rather, as space expanded, the conditions within it changed, and with those changing conditions came changes in what forms of matter and radiation could stably exist. This cooling allowed a succession of physical transitions. The universe was not merely becoming less hot in a general sense. It was passing through thresholds at which the behavior of nature changed. Eventually, quarks became confined into composite particles such as protons and neutrons. This transition was crucial because without it, the later history of ordinary matter would never have unfolded. The building blocks of atomic nuclei had to emerge before any later chemistry or astrophysics could exist. Yet even after protons and neutrons appeared, the universe was still far too hot and energetic for stable atoms. It remained a place dominated by radiation and elementary interactions. not by the quiet structures of later cosmic life. Another subtle and profound issue also belongs to these first moments: the asymmetry between matter and antimatter. According to the best current understanding, the early universe should have produced matter and antimatter in closely related ways. Yet the observable universe today is overwhelmingly made of matter. If matter and antimatter had existed in exactly equal amounts under perfectly symmetric conditions, they would largely have annihilated one another, leaving behind a very different cosmos dominated by radiation, with little ordinary matter remaining to form stars, planets, or living beings. The fact that matter survived in excess means that some asymmetry must have operated in the early universe. Scientists do not yet possess a complete explanation for this process, but it is one of the most important open questions in fundamental physics. It belongs naturally to the story of the first moments, because that is where the conditions determining the later material universe were set. As cooling continued, the universe reached the stage in which protons and neutrons could begin forming the first atomic nuclei. This period is known as primordial nucleosynthesis. NASA's current descriptions emphasize that in the first minutes, collisions among protons and neutrons produced the earliest light elements, especially hydrogen and helium, along with trace amounts of a few others. This was a major turning point. The universe still did not contain ordinary atoms in the later sense because electrons were not yet bound into stable neutral structures. But the cores of future atoms were beginning to exist. The chemical foundation of the later cosmos was being laid down astonishingly early. What is striking here is how much of the later universe depended on these brief early conditions. The abundance of helium in the cosmos, for example, is not just a detail of stellar evolution. A large fraction of it was already determined in the early universe before the first stars ever ignited. This is one reason the hot early universe model is so scientifically powerful. It does not merely offer a dramatic origin story, it makes measurable predictions about what the universe should contain, and those predictions can be compared with observation. Yet despite the appearance of nuclei, the universe was still not transparent. For a long time after these first moments, free electrons remained abundant, and light could not travel unhindered across cosmic distances. The universe was more like a glowing fog than a clear expanse. Photons scattered repeatedly from charged particles, making the cosmos opaque. This later led to the release of the cosmic microwave background, which belongs to a later chapter in the story. But it is important to notice here that the early universe passed through a long interval in which light was present everywhere, but free sight, in the ordinary sense, did not yet exist. The cosmos was full of radiation, yet not yet visually open. There is a temptation, when thinking about the first moments, to imagine them as a tiny miniature version of later cosmic scenes, small particles flying through dark space, perhaps like sparks in a chamber. But that image is misleading. The early universe was not a collection of objects moving through emptiness. It was a total state of reality in which the ordinary separations between objects, background, and medium were not yet established in the familiar way. Everything was immersed in extreme conditions. The universe had not yet become a place of islands and darkness. It was closer to a nearly uniform sea of energy and matter undergoing rapid change. For this reason, the first moments of the universe are often described through phases rather than through scenery. One phase gives way to another as the cosmos expands and cools. A brief stage of accelerated expansion sets the initial large-scale conditions. A hot, dense plasma fills the universe. Fundamental particles interact intensely. Quarks become bound into protons and neutrons. Light nuclei form. The universe continues to expand, carrying within it the seeds of all later structure. Each step is part of a physical narrative, and each depends on the laws of nature, acting under conditions far more extreme than anything in everyday experience. What makes this story scientifically beautiful is that it is neither pure speculation nor total certainty. It is a layered reconstruction. Some parts are anchored by direct observation of relics, such as the cosmic microwave background and the large-scale distribution of matter. Some parts are supported by the success of nuclear and particle physics under extreme conditions. Some parts, especially inflation's detailed mechanism and the origin of matter-antimatter imbalance, remain incomplete. But the overall picture is coherent. The universe began in a state radically unlike its present one, and its earliest moments established the conditions for everything that followed. There is also something humbling in the fact that the first moments are still partly hidden from us. Science has traced the young universe with extraordinary success, yet the deepest origin remains partly veiled behind the limits of current theory. That is not a weakness of cosmology. It is a sign that we are looking toward the edge of what present knowledge can hold. The early universe is both known and not fully known, illuminated and still shadowed. And perhaps that is why this chapter carries a quiet existential weight. The first moments of the universe were not grand in the human sense. They were not composed for an audience, and they did not unfold with meaning written plainly across them. Yet from those severe and nearly featureless conditions came every later star, every planet, every living cell, and every moment of consciousness that would one day look back and ask how it all began. There is something almost tender in that thought, that the warm, familiar world of human experience emerged from a beginning so unlike comfort, and that even now, in the silence of night, your own brief awareness is part of that ancient unfolding. Chapter 5. How Matter Emerged from the Primordial Fire. In the earliest accessible stages of cosmic history, the universe was not filled with the kinds of matter we know from ordinary experience. There were no atoms, no molecules, no grains of dust, no stones, no oceans, no living cells, and no planets waiting in the dark. There was instead an extreme and crowded state of energy, radiation and elementary particles, changing with extraordinary speed as space expanded and conditions cooled. To say that matter emerged from this primordial fire is not only a poetic phrase. It is a scientific description of one of the greatest transitions in nature, the passage from a universe too hot for stable, familiar structures to a universe able to preserve the basic ingredients from which all later structure would be built. This emergence did not happen all at once. Matter, in the everyday sense, is the result of several successive transitions. At first, the universe contained immense energy densities and particles interacting so rapidly that many distinctions familiar to us were not yet durable. Quarks and gluons, which in the present universe are confined inside protons and neutrons, could exist in a deconfined state known as quark-gluon plasma. Certain summaries describe this phase as one in which hadronic boundaries disappear under extreme temperature and density. and they note that heavy ion collisions can recreate similar conditions in the laboratory to study how this state expands and cools. In other words, the earliest universe was not simply hot. It was hot enough to place matter in a fundamentally different phase from the one we encounter now. As the universe expanded, it cooled, and cooling allowed change to become selective. Not every structure can survive at every temperature. In a sufficiently energetic environment, collisions are so violent and frequent that composite forms are torn apart as soon as they appear. The early universe, therefore, had to pass below certain thresholds before more durable arrangements of matter could persist. One of the most important of these transitions was the confinement of quarks into hadrons, especially protons and neutrons. This step matters because protons and neutrons are the raw material of atomic nuclei. Without them, later chemistry would have had no stable foundation. CERN's descriptions of quark-gluon plasma emphasize that studying how this plasma cooled and gave rise to particles helps explain how the matter composing today's universe progressively emerged. But even the appearance of protons and neutrons was not enough to guarantee a material universe like ours. Another deeper problem stood in the way. According to the basic symmetries of known physics, the early universe should have produced matter and antimatter in closely matched ways. Antimatter is not imaginary or speculative. It is real, measurable, and well established in laboratory physics. Yet the observable universe is overwhelmingly made of matter. CERN's public explanations emphasize the puzzle clearly. If the Big Bang had produced exactly equal amounts of matter and antimatter, the two would have annihilated one another very efficiently, leaving a universe dominated by radiation rather than ordinary material structure. The fact that stars, planets, gas clouds, and people exist means that a tiny excess of matter over antimatter must have survived. CERN describes the current best broad explanation as an unknown mechanism that created roughly one extra matter particle for about every billion antimatter particles, so that after mutual annihilation, a small residue remained. That surviving excess was tiny in relative terms, but cosmically decisive. Almost all of the matter and antimatter in the young universe annihilated into radiation, yet not perfectly. A slight imbalance remained, and that residue became the substance of all later ordinary matter. In that sense, the universe we inhabit depends on an asymmetry so small that it seems almost negligible when stated abstractly, and yet so important that without it there would be no long-lived stars, no rocky planets, and no chemistry complex enough for life. Particle data group reviews describe this baryon asymmetry as one of the central conditions any successful account of the early universe must explain, and they note that generating such an asymmetry requires very specific physical ingredients. The details remain an open frontier of physics, but the empirical fact of matter's survival is not in doubt. Once enough matter survived annihilation, the next step was to determine what kinds of nuclei could actually form in the young universe. Protons and neutrons did not immediately assemble into complex structures the moment they existed. The universe was still full of extremely energetic radiation. Photons were so numerous and so powerful that any fragile bound state could easily be broken apart again. This made the emergence of nuclei a delicate race between construction and destruction. The Particle Data Group's review of Big Bang nucleosynthesis explains that the first crucial step is the formation of deuterium, a nucleus made of one proton and one neutron. Yet, Production of deuterium was delayed because high-energy photons kept photodissociating it almost as soon as it formed. Only after the universe cooled enough did deuterium become stable enough for further nuclear reactions to proceed. This delay is often called the deuterium bottleneck, and it was one of the main gates through which matter had to pass on its way toward a more structured cosmos. When that bottleneck finally opened, primordial nucleosynthesis began in earnest. NASA's Summary of Cosmic History explains that in the first minutes, protons and neutrons collided and produced the earliest elements, chiefly hydrogen and helium, along with traces of lithium and beryllium. The Particle Data Group review adds important detail. Nearly all neutrons ultimately ended up bound inside helium nuclei, because helium is the most stable light nucleus easily formed under those conditions. This is why a significant fraction of the ordinary matter in the universe became helium very early, while most of the remainder stayed as hydrogen. The universe did not spend long manufacturing a broad periodic table. It produced a small set of light nuclei and then moved on. This limited outcome was not an accident. The early universe was excellent at making some things and poor at making others. It could produce light nuclei during a relatively brief window when temperatures and densities were suitable, but it could not efficiently build the heavier elements familiar from rocks, biology, and planets. Particle Data Group reviews explain that the absence of stable nuclei with certain intermediate mass numbers blocks a smooth bridge from helium to much heavier nuclei under primordial conditions. As a result, the early universe made mostly hydrogen and helium, plus tiny amounts of a few other light species, and then nucleosynthesis effectively stopped as expansion reduced the density and temperature further. The cosmos had laid down its initial material inventory, but the richer chemistry of carbon, oxygen, silicon, iron, and the rest still belonged to the future work of stars. This is one of the most elegant features of modern cosmology. The early universe did not need to make everything. It only needed to make enough. Hydrogen would become the long-burning fuel of stars. Helium would become both a relic of the first minutes and a participant in stellar evolution. The heavier elements would be forged later in stellar interiors and explosive events. Matter emerged in stages, and each stage prepared the conditions for the next. The primordial fire did not directly build worlds. It built the simplest, lasting ingredients from which worlds could eventually arise. Even after nuclei formed, the universe was still not a place of ordinary atoms. It remained filled with free electrons, and light could not yet travel freely over long distances because it scattered constantly from charged particles. ESA explains that for hundreds of thousands of years, matter and light were tightly coupled and the universe was opaque. So by the end of primordial nucleosynthesis, the universe had stable light nuclei, but not yet neutral atoms and not yet transparent space. Matter had emerged in one important sense, but not yet in its fully familiar form. The cosmic story was still in preparation. The nuclei existed first, atoms would come later. What makes all of this scientifically powerful is that it is not a loose narrative imposed after the fact. Big Bang nucleosynthesis makes quantitative predictions about the abundances of the light elements, and those predictions can be compared with astronomical observation. Particle Data Group reviews note that the abundances of deuterium and helium agree strikingly well with the standard cosmological model and with independent measurements of baryon density from from the cosmic microwave background. This agreement matters because it connects different eras of cosmic history. The first minutes of the universe and the much later release of the cosmic background light tell a consistent story about how much ordinary matter the universe contains. There is something quietly astonishing in the fact that modern scientists can reconstruct this story at all. No one watched the first nuclei form with ordinary eyes. No one stood near the young universe taking measurements directly from within its blazing plasma. Instead, physicists combined nuclear theory, particle physics, astronomical abundances, and observations of relic radiation. From those pieces, they inferred how matter crossed the threshold from instability toward permanence. This is one of science's most beautiful habits. It learns to read the present as a record of vanished conditions. The hydrogen in interstellar space and the helium in stars are not merely substances around us. They are surviving testimony from the earliest material chapter of cosmic history. And yet this chapter remains incomplete in one important way. Scientists understand the broad sequence by which stable ordinary matter emerged, but they do not yet fully understand why matter won its tiny victory over antimatter in the first place. That unanswered question gives the story a frontier. The universe clearly passed through a stage that favored matter just enough to leave a residue. But the full mechanism remains one of the major unsolved problems in physics. This means that the material world around us is both understood and still partly mysterious. We know a great deal about how the primordial fire cooled into durable substance, and still not everything about why there was any durable substance left at all. Perhaps that is what makes the emergence of matter feel more than technical. Everything solid, warm, and familiar in human life depends on a sequence of events that could easily have gone another way. A slight asymmetry survived annihilation. A narrow window allowed light nuclei to form. Expansion and cooling preserved rather than erased what had briefly become possible. From that fragile beginning came the long material history of stars, planets, oceans, bodies, and minds. There is something quietly existential in realizing that the ordinary world is not the default state of reality, but the outcome of a rare and delicate unfolding. And tonight, when life feels immediate and crowded, it may help to remember that the matter of your body belongs to a story far older than worry. The universe once burned so fiercely that nothing familiar could last, and still, over time, it became gentle enough for stable things to exist. In that sense, even your brief, quiet presence here is part of the old victory of matter over fire. Chapter 6. When light finally broke free. For a long stretch of the early universe, light existed everywhere, and yet the universe was not transparent in the way we usually imagine space to be. This is one of the strangest features of cosmic history. We often picture light as the thing that reveals reality, the thing that makes visibility possible. But in the young universe, the presence of light did not mean clear sight. Space was filled with radiation, yet it was more like a glowing fog than an open expanse. Photons were constantly scattered by free electrons, changing direction again and again, unable to travel far without interruption. The universe was bright in a physical sense, but visually closed. That condition followed naturally from the state reached after the earlier phases of nucleosynthesis. Light nuclei already existed, but ordinary neutral atoms did not yet endure. The universe remained hot enough that electrons could not stay bound to nuclei for long. If an electron briefly joined a proton, a sufficiently energetic photon could quickly break that union apart again. Matter therefore remained ionized, meaning that much of it was still in the form of charged particles. As long as free electrons were abundant, photons kept interacting with them through scattering, and this prevented light from moving freely across great distances. NASA's summaries of the early universe emphasize exactly this point. Only after hydrogen and helium nuclei captured electrons into neutral atoms could light finally stream through space without being scattered over and over. This transition is known as recombination, though the name can be slightly misleading. It sounds as though stable atoms had existed before and were merely being reassembled. But on cosmic scales, it refers to the era when electrons and nuclei combined into neutral atoms in a lasting way. Once this happened widely enough, the optical character of the universe changed. Space became transparent. ESA describes recombination as the epoch that marks when the universe became transparent to light, and it identifies the radiation reaching us from that time as the cosmic microwave background. That is why this chapter matters so much. It tells the story not simply of light existing, but of light finally escaping. The phrase "light broke free" is useful as long as it is understood carefully. It does not mean that all light had previously been trapped inside some boundary and then burst outward at one dramatic instant. Rather, it means that the average distance a photon could travel without scattering became enormously larger. Before recombination, the young universe was opaque because photons were tightly coupled to charged matter. After recombination, that coupling weakened drastically. The photons were no longer constantly deflected by free electrons, so they could propagate across the universe for immense stretches of time. The radiation released into free travel at that stage is what we now observe, after being stretched by cosmic expansion, as the cosmic microwave background. This moment is sometimes described as the appearance of the oldest light we can directly observe. That phrasing is scientifically important. It does not mean it was the first light that ever existed in the universe. Photons were present long before recombination. What changed was not their existence, but their freedom of motion. The cosmic microwave background is the oldest light we can still see precisely because earlier light could not travel cleanly through the opaque plasma. Recombination created a visible surface in time, often called the last scattering surface. What we observe today is not a photograph of the absolute beginning, but a relic image of the universe at the time when photons last scattered often enough to keep the cosmos opaque. ESA describes the background as the ultimate snapshot of the universe at recombination, and that is one of the most accurate ways to imagine it. There's a subtle beauty in this. The early universe did not gradually fade from cloudy to clear in a casual, everyday way. The transition was governed by thermodynamics, atomic physics, and the changing density of the expanding cosmos. As space expanded, the average energy of the radiation field dropped. This made it harder for photons to keep tearing electrons away from nuclei. Once conditions crossed the necessary threshold, neutral atoms could persist in enormous numbers. Hydrogen played the central role, with helium also contributing. NASA's early universe explanations emphasize that ionized hydrogen and helium attracted electrons and became neutral atoms, and this allowed light to move freely for the first time because photons were no longer scattering off abundant free electrons. The universe that emerged from recombination was still simple by later standards. There were no stars yet. No galaxies had lit up the darkness. The cosmos entered a long period often called the Dark Ages, in which neutral hydrogen, dark matter, and relic radiation dominated the large-scale environment. NASA materials describing this era note that the universe was considerably simpler then, and therefore forms an especially valuable laboratory for cosmology. But it is important not to imagine this interval as empty. The universe contained structure in seed form. Tiny variations in density were already present, and gravity continued slowly amplifying them. The photons that had broken free preserved a record of those slight irregularities, which is one reason the cosmic microwave background became such an extraordinary scientific treasure. Those slight variations matter because the background is not perfectly uniform. It is astonishingly smooth overall, but not exactly the same in every direction. ESA explains that the density of matter at recombination was nearly the same everywhere, with only tiny changes from place to place, and that temperature fluctuations in the cosmic microwave background reflect the pattern of structure present in matter right when the background was released. These minute fluctuations later grew into the much richer cosmic architecture of stars, galaxies, and clusters. In that sense, when light finally broke free, it did not merely illuminate the universe as it was. It carried forward a map of what the universe might become. Another important piece of this story involves sound, though not sound in the ordinary human sense of pressure waves moving through air. Before recombination, the tightly coupled plasma of photons and matter could support pressure waves, often called baryon acoustic oscillations. NASA's visualization material explains that gravity pulled matter inward while radiation pressure pushed outward, creating oscillating waves in the plasma. Once neutral atoms formed and particles stopped repelling and scattering in the same way, those waves effectively froze in place, leaving traces imprinted on the later distribution of matter. This means recombination did not only release light, it also locked in a fossil pattern of earlier motion, preserving evidence that cosmologists can still measure in the large-scale universe today. The cosmic microwave background is therefore more than an afterglow. It is both relic radiation and a record of physical conditions in the early universe. Its temperature, its slight anisotropies, and its polarization all provide information about the content and history of the cosmos. ESA's Planck mission and earlier NASA missions such as COBE and WMAP turned this background from a broad confirmation of the hot early universe into one of the most precise observational foundations of modern cosmology. By measuring the background carefully, scientists have inferred the geometry of the universe, the abundance of ordinary matter, the abundance of dark matter, and the details of primordial fluctuations with remarkable precision. Although that deeper measurement story belongs partly to the next chapter, it begins here, at the moment light became free enough to preserve a readable cosmic record. It is also worth noting that transparency did not remain absolute and untouched forever. Much later, when the first stars and galaxies formed, their energetic ultraviolet radiation reionized much of the neutral hydrogen between galaxies. ESA describes this reionization as a later phase in which bubbles of ionized gas expanded and merged, altering the journey of cosmic microwave background photons in subtle ways. This does not undo recombination. Rather, it shows that the universe has passed through multiple changes in ionization state over its history. Recombination made the universe transparent enough for relic light to travel. Reionization, long afterward, marked the beginning of a more structured and luminous cosmic era. What makes the release of the cosmic microwave background so powerful is that it joins ordinary atomic physics to the largest possible scale. The same basic fact that electrons can bind to nuclei when conditions are cool enough became a turning point for the whole universe. That is one of the quiet wonders of cosmology. Vast events do not always depend on exotic principles alone. Sometimes they depend on familiar physics operating everywhere at once. Recombination was not a theatrical cosmic explosion. It was a universal change of state, and yet it transformed the very possibility of visibility across the cosmos. There is also a deeper lesson in the fact that the oldest directly observable light comes from a time when the universe was still so simple. We do not first see the cosmos when it is already filled with galaxies, colors, and recognizable forms. We first see it as a nearly uniform field with delicate irregularities. Complexity comes later. The background shows us a universe that is still waiting, in a sense, for structure to ripen. It is like reading the first visible page of a very long story and finding that almost everything familiar is still only implied. Perhaps that is part of why this chapter feels quietly moving. There was a time when light existed, but could not yet travel freely, when the universe was radiant and still hidden from itself. Then, as conditions softened, visibility became possible. The oldest light we can see began its journey then and has been crossing the cosmos ever since, carrying a memory from an age before stars. There is something existential in that image, that reality itself had to pass through a long opacity before anything like clear vision could emerge, and that even now our own understanding arrives late, reading ancient light that set out long before there were eyes to receive it. And when the day feels crowded and hard to read, it can be calming to remember that the universe also had its era of fog. Clarity did not exist at first. It arrived slowly, when conditions were finally gentle enough to let light continue on its way. Perhaps rest can work that way too. Chapter 7. The Cosmic Microwave Background, the baby picture of the universe. By the time light finally began traveling freely across the universe, something extraordinary had happened. The cosmos had produced not only a relic glow from its early history, but also a record. That record still surrounds us now. It does not arrive as visible starlight or as the bright radiance of galaxies. It arrives as faint microwave radiation spread across the sky, almost perfectly uniform, yet carrying tiny differences from place to place. This is the cosmic microwave background, often described as the baby picture of the universe. The phrase is memorable not because the early universe looked cute or small in any ordinary sense, but because this radiation gives us the earliest direct image of the cosmos that light can provide. This background is one of the most important discoveries in all of science, because it transformed the Big Bang from a compelling idea into a model supported by direct physical evidence. Before its discovery, the expanding universe already suggested that the cosmos had once been hotter and denser than it is now. But suggestion is not the same as confirmation. A scientific theory becomes far stronger when it leaves behind a measurable trace that can still be found later. The cosmic microwave background is exactly that kind of trace. It is ancient radiation that has been traveling through the universe since the epoch when matter and light stopped scattering so intensely and the cosmos became transparent enough for photons to move freely across enormous distances. What makes this radiation especially powerful is that it is not local. It does not come from one star, one galaxy, or one special direction in the sky. It fills the entire sky. Wherever astronomers point their instruments, they find it. This is one of the reasons it became such strong evidence for an early hot universe. A local source could be explained away as an unusual cloud, a nearby structure, or some unknown property of our region of space. But an almost uniform background present in every direction points to something far more fundamental. It suggests that the whole universe once passed through a shared physical state, and that the remnants of that state still surround us. The story of how this was recognized is one of those moments in science where observation and theory meet with unusual elegance. In the middle of the 20th century, physicists working on cosmology had realized that a hot early universe should leave behind relic radiation. As the universe expanded, that radiation would cool and stretch into longer wavelengths, but it would not disappear. It should still be present as a faint background. This was a bold prediction because it meant that the early universe, though gone, had not vanished without a trace. It had left an afterglow. When Arno Penzias and Robert Wilson accidentally detected an unexplained microwave signal coming from all directions, they had found exactly the kind of radiation that the hot Big Bang picture seemed to require. The discovery mattered not only because the radiation existed, but because of its character. It was remarkably close to uniform. That uniformity told scientists something important about the early universe. On large scales, the young cosmos must have been extraordinarily smooth, with nearly the same temperature and density in region after region. If the early universe had been violently irregular on the largest scales, the background would likely have shown much stronger differences from one part of the sky to another. Instead, what astronomers found was a universe that, in its youth, was almost the same everywhere. And yet not perfectly the same. This is what makes the cosmic microwave background so scientifically rich. If it had been absolutely uniform, then it would have confirmed an early hot phase, but it would also have raised another puzzle. How could stars, galaxies, and clusters ever form in a universe with no initial unevenness at all? Gravity needs something to work with. It can amplify differences, but it cannot build large cosmic structure out of perfect sameness. The great triumph of later cosmic microwave background measurements was that they revealed the tiny fluctuations hidden within the almost uniform glow. These minute variations in temperature correspond to very slight differences in density in the early universe. They are the seeds from which later structure grew. This is why the baby picture metaphor works so well. The cosmic microwave background shows the universe in an early stage before its mature features had appeared. There are no galaxies visible in the background map. No glowing nebula, no grand spiral forms, no black holes, no planets. What we see instead is a nearly featureless young universe with small irregularities, the faint hints of everything that would come later. It is not a portrait of the cosmos in its dramatic adulthood. It is a picture of potential. It shows a universe that has not yet formed its great visible architecture, but already contains the subtle patterns from which that architecture will emerge. The first major space mission to map this background in a decisive way was Kobe, the cosmic background explorer. Kobe confirmed with great precision that the background radiation has the spectrum expected of thermal radiation from a hot early universe, which was already a profound result. But even more famously, Kobe detected the intrinsic anisotropies, the tiny temperature variations across the sky. Those fluctuations were extremely small, yet cosmologically enormous in meaning. They showed that the early universe was not perfectly smooth. They offered direct evidence of the primordial irregularities needed for structure formation. This was why people began speaking more vividly of the first baby picture of the universe. It was the first time humanity had seen the faint texture of the early cosmos written across the sky. Later missions sharpened this picture dramatically. WMAP, the Wilkinson Microwave Anisotropy Probe, produced a far more detailed full-sky map of the background and measured its tiny differences with much higher precision. This allowed cosmologists to determine fundamental properties of the universe with extraordinary confidence. The cosmic microwave background was no longer just a confirmation that the Big Bang model was broadly right. It became a precision instrument for cosmology. By studying the size, distribution, and statistical pattern of the hot and cold spots in the map, scientists could infer the geometry of the universe, the amount of ordinary matter, the amount of dark matter, and the overall contents of the cosmos. A faint microwave glow had become one of the most powerful tools ever used to study reality on the largest scale. Then came Planck, which carried this work even further. Planck mapped the cosmic microwave background with still greater sensitivity and resolution, revealing an even sharper picture of the early universe. The Planck data made it possible to extract cosmological parameters with remarkable accuracy and to test the standard cosmological model in extraordinary detail. The mission also showed how much information had always been hidden inside what at first looked like a nearly uniform field. The universe had been speaking quietly through the background all along. It simply took instruments precise enough to hear what it was saying. One reason the cosmic microwave background is so informative is that the early universe behaved as a physical system with structure that can be read statistically. Before recombination, matter and radiation were tightly coupled in a plasma. Pressure and gravity interacted within that plasma, creating oscillations that left an imprint on the background. Those imprints can still be measured today. The hot and cold spots are not random decoration. They reflect real physical processes in the young universe. When cosmologists analyze the background, they are not merely admiring an old image. They are decoding a fossil pattern of sound-like waves, density variations, and early conditions that later shaped the visible universe. Another striking feature of the cosmic microwave background is how far back it lets us see, and also how clearly it marks a limit. It is the oldest light we can observe directly, but it is not a view of the absolute beginning. It comes from the time when the universe first became transparent to radiation. Anything earlier is hidden behind the opacity of the primordial plasma. In that sense, the cosmic microwave background is both a revelation and a boundary. It opens a window into the early universe, but it also reminds us that direct vision has limits. To understand earlier epochs, cosmologists must infer rather than directly observe. The background is therefore like a horizon in time, the farthest screen of ancient light that still reaches us. This is part of what makes the background so philosophically powerful. It shows that the universe can preserve memory, The cosmos does not merely change and erase itself. Under the right conditions, it keeps traces. The microwave background is a memory from an age before stars, before galaxies, before planets, before chemistry as we know it. It is the surviving radiation of a universe still young, still simple, still waiting for complexity to unfold. And that memory is not stored in a book or a mind. It is written into the sky itself. There is also something deeply humbling in the scale of the achievement. Human beings on one planet around one ordinary star learn to detect a whisper from the early universe, not by traveling backward in time and not by leaving the cosmos to view it from outside, but by building instruments sensitive enough to measure a faint relic glow that fills all space. This is one of the great, quiet triumphs of science. It shows that knowledge does not require a privileged cosmic position. It requires patience, inference, and the willingness to take tiny signals seriously. The cosmic microwave background also changed how scientists think about the connection between simplicity and complexity. The early universe revealed in the background is, in one sense, much simpler than the universe we see today. Its matter was distributed far more smoothly. Its visible features were few. Yet hidden inside that simplicity were the first conditions for all later richness. The galaxies, stars, planets, and eventually living beings did not appear in spite of the early universe's smoothness. They emerged because that smoothness was not complete. The smallest departures from uniformity carried the future within them. That may be one of the most moving lessons in cosmology. The universe did not begin with grand visible drama already assembled. It began with subtle differences, barely there, almost lost inside sameness. Over time, those tiny departures became structure, light, complexity, and life. There is something existential in that thought, that vast futures can be hidden inside small beginnings, and that what looks nearly featureless at first may still contain the seeds of everything that follows. And tonight, when the mind feels crowded with immediate things, it may help to remember that the sky still carries a memory from before stars existed. The oldest light is still moving gently around us, patient and faint, preserving the image of a universe that had only just begun to become itself. In that quiet afterglow, there is something strangely comforting. Even the cosmos once had a childhood. Chapter 8. How the first stars and galaxies began to form. After the cosmic microwave background was released, the universe entered a quieter phase. It was no longer an opaque plasma, and light could now travel freely across immense distances. But it was not yet the bright and structured cosmos we know today. There were still no stars burning in the darkness, no galaxies shining across space, and no heavy elements enriching the gas. The universe had become transparent, but it had not yet become luminous in the familiar astronomical sense. For a long interval, it was filled mainly with neutral hydrogen and helium, along with dark matter, faint relic radiation, and tiny density variations left over from earlier times. This period is often called the cosmic dark ages. The phrase dark ages can sound more dramatic than the physics requires, but it captures something real. The universe during this era was not empty, and it was not inactive. Gravity was still at work everywhere, slowly amplifying the slight unevenness inherited from the early universe. Yet there were no stars yet to flood space with fresh visible and ultraviolet light. The cosmos contained matter and structure in seed form, but not the great luminous objects that later made the universe visually rich. In that sense, this was a waiting period, though not a passive one. It was a time when the simplest ingredients of the universe were gradually being organized into the first sites of collapse. Dark matter played a central role in this process. Astronomers do not yet know the fundamental identity of dark matter, but the standard cosmological picture holds that it provided much of the gravitational scaffolding or later structure formation. Because dark matter does not interact with light in the ordinary way, it could begin clumping under gravity without being delayed by the same radiative effects that shaped ordinary matter in the earliest eras. Small dark matter concentrations, often called halos, grew over time and created gravitational wells into which ordinary gas could fall. ESA's material on galaxy formation emphasizes that the evolution of the earliest galaxies is closely tied to the underlying dark components of the universe, while theoretical work on the first stars describes their birth inside these early gravitational wells. Ordinary matter, however, could not simply fall inward and form stars the instant it entered those halos. A gas cloud forms a star only if it can lose enough energy to contract further. If pressure remains too high, collapse stalls. This is one of the key ideas in star formation across cosmic history, but it was especially important in the early universe because the gas then was extremely simple. It was made almost entirely of hydrogen and helium, with essentially none of the heavier elements that later helped gas cool more efficiently in enriched environments. The first star-forming clouds therefore had to rely on more limited cooling processes than many later clouds would use. Theoretical reviews of population 3 stars emphasize that primordial gas was metal-free and that this strongly affected how the first stars formed. One of the most important cooling agents in that primordial gas was molecular hydrogen. Even in tiny amounts, it could help the gas radiate energy away and sink deeper into gravitational collapse. As gas settled into the first dark matter halos, density increased, temperatures rose, and local conditions sometimes allowed molecular hydrogen to form. That process gave the gas a way to cool enough for collapse to continue. Harvard-based astrophysical discussions of the first stars and early star formation emphasize that the earliest luminous objects likely formed when primordial gas cooled and condensed inside small halos in the young universe. The first stars are often referred to as population 3 stars. They were unlike the stars around us today because they formed from pristine gas that had not yet been enriched by earlier stellar generations. No previous stars had lived and died to create carbon, oxygen, silicon, iron, or the many other heavier elements now common in cosmic matter. The first stars therefore emerged from a universe that was chemically simple in a way no later epoch would ever be again. NASA's recent explanations note that the first stars likely formed from dense regions of hydrogen and helium collapsing under gravity, and that this may have begun only a relatively short time after the Big Bang on cosmic scales. Exactly what those first stars were like remains an active area of research. But theory strongly suggests that many of them were very different from typical stars forming today, because primordial gas cooled less efficiently than metal-enriched gas. The characteristic masses of the first stars may often have been higher. Many models indicate that the earliest stars were frequently massive, hot, and short-lived. Their internal temperatures would have driven intense nuclear fusion, producing powerful ultraviolet radiation. The recent annual review article on the first stars describes population 3 stars as the first generation of metal-free stars and discusses how their properties and impact differed from later stellar populations. Once the first stars ignited, the universe changed in more than one way at once. First, it gained new sources of light beyond the relic glow of the microwave background. Second, it gained the first factories for heavier elements. Inside stellar cores, fusion began turning hydrogen and helium into heavier nuclei. Third, the radiation from these stars began affecting the gas around them. Ultraviolet light from the first luminous sources ionized nearby hydrogen, carving out bubbles of ionized gas in the surrounding neutral medium. This marked the beginning of the era called reionization, when the first stars and galaxies progressively transformed intergalactic space. ESA describes reionization as the period when energetic light from the first stars and galaxies changed the state of gas between galaxies from neutral to ionized again. These first stars also did not live quietly for long. If many of them were indeed massive, then many would have exhausted their fuel relatively quickly and ended in violent deaths, including supernova explosions for at least some mass ranges. Those deaths were cosmically important. They scattered the first heavy elements into surrounding space, changing the chemistry of the gas available for later generations of stars. In this way, the first stars acted as a bridge between a simple universe made mostly of hydrogen and helium and a richer universe capable of more complex cooling, more varied stellar populations, rocky planets, and eventually chemistry suitable for life. ESA's early universe overview explicitly notes that the first stars produced the chemical elements necessary for the later formation of planets and, ultimately, life. Galaxies did not appear all at once as grand spiral systems like the Milky Way. The earliest galaxies were smaller, more irregular, and still assembling. NASA and SA materials on galaxy evolution emphasize that early galaxies differed greatly from many present-day ones, and that small galaxies in the early universe likely merged over time to form larger systems. The first galaxies probably formed as collections of gas, dark matter, and stars gathered inside growing halos. With repeated cycles of collapse, star formation, radiation, feedback, and merger, gradually building more substantial structures. This process was not smooth. When stars formed, they also pushed back on their surroundings. Radiation, stellar winds, and supernova explosions could heat gas, drive it outward, and regulate how efficiently new stars formed. So the first galaxies were not just passive containers where matter accumulated. They were active environments in which gravity tried to gather material, while stellar feedback tried, at least partly, to disrupt or reshape that gathering. This balance between collapse and feedback remains central to galaxy formation today, but it was especially dramatic in the early universe because the first galaxies were still small and comparatively fragile. Current NASA explanations of early galaxies and Webb observations emphasize that astronomers are still learning how those early systems formed and evolved, and that the earliest galaxies were more complex than once expected. One of the great modern advances in this field has come from the James Webb Space Telescope. Because the light from extremely distant early galaxies is stretched into the infrared by cosmic expansion, Webb is especially well suited to observe them. NASA explains that Webb is designed to study the earliest stages of galaxy formation and can reveal stars and galaxies that existed only a few 100 million years after the Big Bang. Recent web results have pushed observations deeper into the early universe and have shown galaxies already in place at surprisingly early times, giving astronomers new data with which to test and refine models of early structure formation. That observational progress matters because the first stars themselves are difficult to detect directly. Individual population. 3 stars may have been rare, brief, and extremely distant, making them elusive targets. Much of what scientists know about them still comes from theoretical modeling and indirect clues, including how early galaxies behave, how reionization unfolded, and how later chemical abundances preserve signatures of the first enrichment events. The first stars may remain partly hidden, but their influence is not. They altered the ionization state of the universe, enriched the gas, and helped initiate the chain of events leading to the larger galaxies seen later. As more stars formed and more galaxies assembled, the isolated ionized bubbles around early luminous regions began to grow and merge. Over time, much of intergalactic hydrogen became ionized, and the universe changed from mostly neutral back to largely ionized on large scales. NASA's Webb results indicate that galaxies supplied enough energetic radiation to transform the early universe over hundreds of millions of years. And ESA's summaries place this transition squarely in the epoch when the first stars and galaxies emerged from the Dark Ages. This means the first stars and galaxies did not merely appear within the universe as it already was. They changed the physical state of the universe around them. What makes this chapter so remarkable is that it marks the beginning of visible cosmic architecture. Before this stage, the universe had history, matter, relic light, and structure in seed form. After this stage, it began to produce engines of fusion, sources of ultraviolet radiation, the first episodes of chemical enrichment, and the earliest galactic systems. The universe was no longer only a place of conditions. It had become a place of objects, not yet the mature objects of later epochs, but the first true luminous builders of everything that followed. There is something quietly existential in that transformation. For a very long time, the universe was dark, simple, and waiting. Then, from tiny unevenness and slow gravitational patience, the first stars ignited and the first galaxies began to gather. Light returned not as a relic from the past, but as a new act of creation inside the cosmos itself. And from those first brief fires came the heavier elements, the richer chemistry, and the long chain of structure that would one day make planets and living minds possible. In that sense, the night sky is not just full of distant objects. It is the late result of a universe that slowly learned how to shine. Chapter 9. What the Big Bang Theory can explain and what it still cannot. But a mature scientific theory is not one that claims to answer every possible question. It is one that explains a wide range of observations with clarity, precision, and internal consistency, while also making clear where its reach begins to fade. The Big Bang Theory is powerful precisely in that way. It is one of the most successful frameworks in all of science, not because it solves every mystery about existence, but because it explains an enormous amount about the history of the observable universe, and does so in ways that can be tested against evidence. At the same time, it leaves some of the deepest questions still open. To understand the Big Bang properly, it is important to hold both truths at once. It is remarkably successful, and it is not complete. What the theory explains best is the large-scale evolution of the universe from an early hot, dense state onward. It explains why distant galaxies, on average, are receding from one another on the largest scales. It explains why the universe contains a faint background of microwave radiation filling the sky in all directions. The cooled relic of a time when light first began traveling freely across space. It explains why the cosmos contains large amounts of hydrogen and helium and only trace amounts of certain other light elements produced in the first minutes of cosmic history. It also explains why the universe today contains structure at all, because slight irregularities in the early cosmos could grow under gravity into the stars, galaxies, and clusters we now observe. These are not minor achievements. They are broad and interconnected successes that link theory to observation across immense ranges of scale and time. One reason these successes matter so much is that they do not stand alone. The evidence fits together. Cosmic expansion tells us that the universe changes with time. The cosmic microwave background tells us that it passed through a hot, dense, opaque phase and later became transparent. The light element abundances tell us that nuclear reactions occurred in the young universe under specific physical conditions. The large-scale distribution of galaxies tells us that tiny early fluctuations really did grow into later cosmic structure. These are different kinds of evidence, gathered through different methods, and yet they point toward the same broad picture. When several independent lines of observation all converge on one history, confidence in that history becomes much stronger. The theory is especially impressive because it allows precise prediction. It is not merely a vague statement that the universe used to be hotter. It predicts that a relic radiation field should remain, and observations found exactly such a background. It predicts a narrow pattern for the primordial abundance of light nuclei, and astronomical measurements align strikingly well with those expectations. It predicts that the early universe should have been nearly uniform, but not perfectly smooth, and the cosmic microwave background shows precisely that kind of structure. This predictive success is one of the central reasons the Big Bang framework became the standard model of cosmology. It does not merely retell what is already known. It organizes the known into a coherent physical history and successfully anticipates what should be found. But this is also the point where an important distinction must be made. The standard Big Bang model is best understood as a theory of the universe's early evolution, not a complete explanation of ultimate origins in the deepest possible sense. It tells us how the observable universe changed from a very early hot, dense phase into the much cooler, structured cosmos we now inhabit. It does not by itself fully explain why the universe began in that state, whether there was something before it, or whether the word before even makes physical sense at the deepest level. Those questions are not avoided because they are uninteresting. They remain open because current physics has not yet resolved them. One of the major places where this incompleteness appears is inflation. Inflation is a leading idea that proposes a brief era of extremely rapid early expansion before the hot, dense phase usually discussed in simpler Big Bang summaries. It helps explain why the large-scale universe appears so nearly flat, why widely separated regions have such similar average properties, and how tiny primordial fluctuations may have arisen and been stretched to cosmic scales. In that sense, inflation helps the broader cosmological picture immensely. Yet the Big Bang framework alone does not tell us exactly what field or mechanism drove inflation, whether inflation happened in the simplest proposed form or how inflation itself began. So inflation is both a success and a frontier. It improves the explanatory power of early universe cosmology, but it also opens further questions rather than closing them. Another major unresolved issue is dark matter. The Big Bang Theory, in its modern cosmological form, works most successfully when the universe contains more than ordinary visible matter. Observations of galaxies, galaxy clusters, and the growth of cosmic structure indicate that most matter is not the familiar atomic material of stars, planets, or bodies. Cosmology can infer how much dark matter there must be in order to match the observed universe, and the background radiation, as well as later structure formation, strongly support its existence. But the Big Bang Theory does not tell us what dark matter fundamentally is. It uses dark matter as part of the best fit description of cosmic evolution, yet its microscopic identity remains unknown. This means the theory can describe the role of dark matter in shaping the universe, without yet revealing the nature of the actor itself. Dark energy presents a similar but even stranger challenge. Observations of distant supernovae and other cosmological measurements show that the expansion of the universe is presently accelerating. In modern cosmology, this behavior is commonly represented by dark energy or by a cosmological constant-like component. The standard model of cosmology incorporates this successfully in order to describe the observed expansion history. But once again, to include something in a model is not the same as to fully understand it. Scientists can measure its effects on cosmic expansion with impressive precision, yet the deeper physical meaning of dark energy remains unsettled. So here too, the Big Bang framework is explanatory and incomplete at the same time. The matter-antimatter asymmetry is another powerful example of both success and limitation. The observable universe is made overwhelmingly of matter. Yet the laws of physics suggest that the early universe should have produced matter and antimatter in closely related ways. If they had been present in exactly equal amounts under perfectly symmetric conditions, they would largely have annihilated one another, leaving a very different universe. The fact that ordinary matter survived means that some asymmetry arose early on. Cosmology recognizes this requirement clearly. It knows that a tiny excess of matter must have remained. But the standard Big Bang model does not yet provide a complete and experimentally confirmed explanation for how that asymmetry came to be. It describes the consequence, while the full cause remains under investigation. There is also the question of the very beginning, and this may be the most philosophically charged limit of all. If we trace the expansion backward using general relativity in a simple way, we reach a state of extreme density and temperature where the known equations indicate a breakdown of the classical description. This is often associated with a singularity, but physicists generally do not treat that as a final literal picture of reality. Instead, it is usually taken as a sign that classical general relativity is no longer enough, and that a quantum theory of gravity is needed. This means that the Big Bang theory does not actually provide a complete account of the absolute first moment in a final sense. It brings us very far back, but not all the way to total understanding. The earliest boundary remains partly veiled, because our deepest theories are not yet unified there. That is an important point to state carefully. It would be wrong to say that the Big Bang theory explains nothing about origins. It explains a great deal about the early physical history of the observable universe. But it would also be wrong to say that it has already solved the final question of why there is a universe at all, or why its earliest conditions were what they were. The theory is strong exactly where evidence can test it, and less complete where evidence becomes harder to access and the known laws of physics reach their limits. There are also more technical tensions within cosmology that remind us science is still alive here. Measurements of the present expansion rate, obtained in different ways, do not yet agree perfectly, a puzzle often called the Hubble tension. Some large-scale anomalies in the microwave background have also been discussed for years, though their significance remains debated. These do not overturn the Big Bang framework. Rather, they show that even a very successful model can still contain unresolved details, parameter tensions, or hints that additional physics may someday refine the picture further. What makes the theory so impressive, then, is not perfection but range. It can connect the behavior of nuclear reactions in the young universe to the distribution of galaxies across billions of light years. It can connect faint temperature fluctuations in the microwave sky to the later rise of cosmic structure. It can tell a unified story stretching from the first minutes of cosmic history to the present large-scale universe. Few scientific frameworks achieve that kind of coherence. The unanswered questions are real, but they stand on top of a foundation that is extraordinarily solid. This balance between knowledge and mystery is one of the most beautiful features of cosmology. The Big Bang theory has shown that the universe has a readable past. It has revealed that cosmic history is not beyond science, and that even the largest questions can sometimes be approached with evidence rather than myth. At the same time, it has shown that the deepest edges of reality do not yield all at once. Every successful answer seems to open a further horizon. The theory explains enough to be astonishing and leaves enough unknown to keep humility alive. Perhaps that is why this chapter carries a quiet existential weight. We live in a universe that can be understood far more deeply than earlier generations ever imagined, and yet not so completely that wonder disappears. The cosmos has allowed itself to be partly read, but not exhausted. There is something strangely comforting in that. Reality is neither fully closed nor fully silent. It speaks, but in layers. And when the day has asked too much of the mind, it may help to remember that not even cosmology demands total certainty before meaning can begin. The universe has already revealed a great deal about how it became what it is, and still keeps some of its first secrets. Perhaps rest can live there too, in that space between what is known and what is still gently waiting. Chapter 10. Was the Big Bang the beginning of everything? By the time we reach this final question, the Big Bang has already changed from a simple popular phrase into something much more precise. It no longer means a giant explosion in darkness. It means that the observable universe has a thermal history, that it expanded from a far hotter and denser early state, and that traces of that history still remain in the sky. But once this scientific picture becomes clear, a deeper question naturally follows. If the Big Bang describes the early evolution of the universe so successfully, does it also describe the absolute beginning of everything? Or does it mark only the beginning of the part of cosmic history that present physics can actually reconstruct? This question sounds simple, but it is not simple in physics. In everyday life, beginnings usually happen within a larger background. A book begins on the first page, but the paper already exists. A storm begins in the sky, but the atmosphere was already there. A human life begins in a world that was waiting beforehand. These habits of thought make us expect that the universe, too, must have begun inside some larger setting. Yet modern cosmology does not automatically grant that picture. The Big Bang model describes the evolution of space-time itself on large scales. That means the question is not merely what event happened first inside the universe, but whether time and space in the form we know them may themselves belong to the history that begins there. Classical general relativity, when applied to an expanding universe and traced backward in a simplified way, leads toward an extreme limit in which density and temperature rise without bound. This is often described as a singularity. But in modern physics, a singularity is usually not treated as a satisfying final answer. It is better understood as a sign that the theory being used has reached the edge of its reliable domain. In other words, the equations are telling us that the classical description is breaking down. The particle data group review makes this point indirectly by emphasizing that the standard Big Bang framework successfully describes the thermal history of the universe, while also facing serious problems with its initial conditions. So the classical singularity is not usually taken as proof that science has already captured the literal first instant of reality in complete form. This is where quantum gravity enters the story, or rather where its absence becomes impossible to ignore. The known laws of physics are extraordinarily successful in their proper domains. Quantum theory describes the very small with extraordinary power. General relativity describes gravity and cosmic structure with extraordinary power. But the earliest conceivable moments of the universe appear to require both at once under extreme conditions, and physics still does not possess a fully confirmed theory that unifies them. That is why responsible cosmology becomes cautious near the beginning. Scientists can describe the universe extremely well after a very early stage, and they can infer much about even earlier phases, but they cannot yet claim complete certainty about the absolute origin in the strongest possible sense. Inflation makes the question even more subtle. In modern cosmology, inflation is a leading idea for an extremely early era of rapid accelerated expansion that helps explain why the large-scale universe appears so smooth and nearly flat, and why small primordial fluctuations existed from which later structure could grow. But inflation does not automatically solve the question of ultimate beginning. It may push the problem one stage earlier. NASA notes plainly that scientists are not sure what came before inflation or what powered it. The particle data group likewise treats inflation as a major extension of the standard picture rather than a completed final origin theory. So even if inflation is correct in broad outline, it may describe an early phase of the universe without yet answering why there was such a phase at all. At this point, science does not offer one agreed answer to what, if anything, came before the hot Big Bang phase. Instead, it offers a landscape of possibilities with very different levels of support. Some approaches suggest that the Big Bang was not the true beginning, but a transition from an earlier state. In such ideas, the hot, dense early universe could have emerged from a bounce, a contraction, or some quantum process that replaced the classical singularity. Other approaches suggest that asking what came before may be partly misguided, because time itself may lose its ordinary meaning near the earliest boundary. In that case, the Big Bang would not be an event preceded by earlier ordinary moments, but the limit at which the very framework of before and after ceases to behave the way human intuition expects. These possibilities are scientifically serious, but none has yet been confirmed in the way that cosmic expansion or the microwave background has been confirmed. This distinction between evidence and speculation is essential. Cosmology does not become more impressive by pretending that every attractive idea is already established. The standard Big Bang model is strong because it is anchored in observation. By contrast, proposals about what preceded it are harder to test directly. Some may eventually gain support through subtle observational signatures in primordial gravitational waves, in the detailed statistics of the cosmic microwave background, or in other relics of the very early universe. ESA has long emphasized that the earliest universe may have generated gravitational wave backgrounds and other traces that could, in principle, reveal physics from otherwise hidden epochs. But until such evidence becomes decisive, these deeper origin models remain possibilities rather than settled knowledge. There is also a conceptual danger here. People sometimes imagine that if the Big Bang was not the beginning of everything, then science must have somehow failed. But that does not follow. A theory can be extremely successful while still describing only part of a larger reality. Newtonian gravity was not wrong because Einstein later found a deeper framework. It was incomplete at the extremes. In the same way, the Big Bang model may remain the correct description of the hot early evolution of our observable universe, even if some deeper theory someday places that evolution inside a wider context. Science often advances not by discarding everything that came before, but by showing where an older theory works magnificently and where a deeper one is needed. Another important point is that the phrase, "the beginning of everything," may combine more than one question. One question is whether our observable universe had an earliest hot, dense phase. The evidence strongly says yes. Another question is whether space-time itself began there in an absolute sense. That remains uncertain. Yet another question is why there is a universe with these laws at all. That is an even deeper problem, and one that may not be answerable by cosmology alone in the ordinary empirical way. Scientific questions must eventually connect to observable consequences. Not every philosophical question does so in the same manner. This does not make the philosophical questions meaningless. It means they may sit partly beyond the present reach of experimental confirmation. So was the Big Bang the beginning of everything? The most careful scientific answer at present is more modest than either a simple yes or a simple no. The Big Bang marks the beginning of the observable universe in the sense that it describes the earliest hot, dense phase from which later cosmic history unfolded. It may also mark the beginning of space-time as we know it, but present physics cannot yet establish that with final certainty. Some models allow earlier states or deeper frameworks. Some suggest that ordinary time may not extend meaningfully beyond the earliest boundary. What science can say confidently is that the universe we observe has a finite thermal history, and that our best tested cosmological model traces that history back to an extremely early state beyond which certainty becomes much harder. There is perhaps something beautiful in that boundary. Cosmology has not left us with pure ignorance, nor with total closure. It has shown that reality is readable far deeper than earlier generations imagined. Human beings have discovered relic light from the young universe, measured its faint fluctuations, traced the expansion of galaxies, and reconstructed much of cosmic history from those clues. And still, near the deepest beginning, the universe becomes quiet again. Knowledge reaches very far, then slows, then stands before a horizon it has not yet crossed. Maybe that is the most honest way to end this journey. The Big Bang may have been the beginning of everything we can presently describe with confidence, or it may have been the first visible chapter of a larger story whose earlier pages remain hidden. Either way, the universe is not a frozen backdrop, but a reality with history, depth, and mystery. And there is something gently existential in that thought, that even the grandest scientific understanding does not erase wonder, but refines it. The cosmos has allowed us to know enough to feel awe, and withheld enough to keep awe alive. When the day has felt small and immediate, it can be calming to remember that your life unfolds inside a universe whose first boundary is still not fully exhausted by human thought. You do not need to solve that boundary tonight. It is enough to rest beneath it and to let the unanswered edge of reality become for a little while not a burden, but a kind of peace. My friend, the story of the Big Bang reminds us that the universe was not born fully formed. It changed slowly, step by step, from heat to light to stars to galaxies and eventually to us. And maybe there is something comforting in that. Even the vast universe became what it is through a long and patient unfolding. If you're still awake, you can stay with me and choose another journey through the cosmos here on Orbital Dreams. And if sleep is already finding you, then rest well and sweet dreams among the stars.